you will find that I have thrown in the next one as well, yeah, just to feel very cruel and this one has a deadline after the break, April 30th, so they're not running in parallel. But the reason I wanted to get it out is give you some flexibility. Yeah? So if you want to build out, work on it over the break, you can. We'll talk a little bit about this later. It's supposed to be, as it says in the sheet, if it comes up. Okay, never mind. Yeah, okay then. So that will. There are a couple of things I need to tell you about doing that. So that's why I released it now, so that you can have some flexibility, get started, and actually finish it when you come back. Okay, so we have looked at options pricing, and we are looking at asking the question, what at time t or time 0 is a fair price of a contract that's drawn on something that happens into the future, and on that contract is some specification about payoff. That over there you will get a certain commitment. Okay? And what we said two things about this. The first thing we said was between now and time t, there is a lot of uncertainty. We do not know what's going to happen. Okay? And that uncertainty is characterized by some stochastic process. This is how life starts. And what we said was we can make some very simplistic assumptions about this, namely it's as a geometric Brownian motion. And we said if we were to make that assumption on very specific, very simple types of options, like a call option, which is European style exercise, which is exercise below here, we can find closed form solutions. Black-Scholes model is one that gave us a closed form solution based on parameters that we can work out at this point in time. And those parameters we work out in that point of time are we observe the risk-free interest rate. We know from the contract the strike price and a drop price at when this is going to be exercised. And we can work out from the market conditions a parameter called volatility. And this is perhaps the only thing that we actually have to estimate from data. Yeah? And what's typically done is to look at, say, some past window of data and estimate this volatility. So that goes in, and we can think then, if this geometric Brownian motion with this set of parameters were to hold, then we worked out that over here, the price that we hit here will have a distribution, and that distribution we said was going to be log normal. So the log of that price was going to have a normal distribution under these assumptions of geometric Brownian motion. Okay? That was the only thing that gave us a handle to be able to write out a closed form formula. Okay? The second method we did was to construct a lattice. We said starting from some point, suppose we have shocks up and down, then from there up and down, we worked a simpler lattice that will revert back to that point. Okay? And then we said, if we were to build the path of that uncertainty on this lattice, yeah, then we can actually calibrate this lattice in terms of the up moving probability, the down moving probability, which is 1 minus the up moving probability. How much does the price go up if you went up? How much does the price go down when you come down? And by choosing a tiny little delta t at which these prices are going to move like that, we can precisely mimic this one. Okay? So those are the two things that we have learned. We will touch on a third way of doing this, and that has to do with simulation-based methods. What we can do is, if we knew that there is a Brownian motion or some other stochastic process, we can simulate sample paths from that process. Okay? So we can say, I'm going to sit at time 0, and I know some things about how this stochastic process might go. I would plug those into a computer program and say, oh, this is 1, possible sample path. Yeah. Along the way, the geometric Brownian motion had epsilon. There will be some uncertainty. That uncertainty would make it go up or down this, and you will get this. Next time I run the simulation, the sample path will be different. So I can keep running this many, many times, and each time I run this, I get a trajectory like this. Okay? With very low probability, this will go down here. Most of the time, it will follow a particular path because I think there is going to be a drift. I think there's going to be a noise added onto that. Drift, noise added, drift, noise added. That's what we would expect to go. Okay? So looking from here, so if I stood here and look to see what happens in the future, yeah, this process of, oops, what have I done? This process of simulating will simulate for me here a probability density. Okay? So I would sit here and say that at time t, all the assumptions that I have made result in a density there. Okay? And what I can then do is to say, oh, suppose if that's the density, which under all these assumptions was log normal, there is one such density. If I had various other complications in my stochastic process, I will have different kinds of densities. I just generate that. Yeah? So I have an empirical density here. I look at this density and say, oh, what's the average of this density? The average of density is here. Okay? For this particular density of sample paths, depending on the contract that you hold, I don't know, K or T or some conditions, yeah, based on those contracts, I will have a payoff density. Yeah. I can sit here and think, if I make these assumptions, over here, the stock price will have a particular distribution. At every point in that distribution, there is a possible payoff. Yeah? That will immediately translate into a payoff density. Then once I have the payoff density, I will ask what would I expect? What's the average of this? Yeah? So the average might be somewhere here. And then what I would work here is e to the minus RT times the average of the payoff. The discounted value of the expected payoff is the fair price of this option. Okay. So discounted expected payoff. Yeah, so that's precisely how we would price options. Okay. So, and this is what we did in the Black-Scholes model as well. This is also what we did in the binomial lattice as well. Yeah. But simulations gives us another way of doing it. Okay? Now, if the distribution is parametric, if it is log normal or some simple one, then I know how to calculate the average. Yeah? And when I calculate the average, I can work back and I can say what the option price should be. When the distribution is not easy, when it is complex, non-parametric and so on, then it's very difficult to calculate an average. We resort to numerical ways of doing it. Okay? And that's another body of literature in options pricing. We will touch on it a little bit today, and I'll give you some hints as to what are the issues that we will look for if you try to do it this way. Okay? And that starts with this expression up there. There's a lot of literature on Monte Carlo integrations. So if you do some advanced machine learning, you might hit this sort of thing as well there as well. The idea is that I want to make an inference. Yeah, my inference is an average or expected value of some function of a random variable. Yeah. The way to interpret it over here is that the function is just 1, because I want to find the expected value of, I want to find the average. Yeah, so there's no function on it. If I want to calculate the variance, the function is squared. Yeah, take away mean. So like that, there's some function. And I want to calculate the expected value. And how do you calculate the expected value? You integrate the function weighted by the probability density over the entire space. Yeah, that's how we calculate expectations. Yeah. And that's a fundamental formula. A lot appears in Bayesian inference types problems. There is some uncertainty which you have captured by a probability density, and you want to make some predictions from that variable whose uncertainty you have captured in the probability density. Yeah? And what do? You do an integral. Okay? So look at a simpler form of this. Think of just some arbitrary integral in the space 0 to 1, g of x. Okay? The way we can think about doing this integral by Monte Carlo simulations is to think of this as calculating the expected value, yeah, of some random variable under the uniform distribution. So we have some function. I want to integrate between 0 and 1. Suppose you tell me that between 0 and 1 there is a random variable of uniform distribution. What is its expected value? That's precisely what this calculation is. Okay? So what we do in this kind of business, in this simple form and that one, is to say, I'm going to approximate the integral by an average of data drawn according to that distribution and the function value computed at that point. Okay? So this is the standard thing that appears again and again in Monte Carlo integration. Monte Carlo integration is to say, I have a function which I want to integrate or find the area under this curve. I think of this as computing the expected value under that probability density. Or in the world of statistical inference, Bayesian inference, you are actually given a probability density, yeah, and you want to compute an expectation of a function of the random variable that's distributed this way. Okay? In either case, in either interpretation, what we want to find is that I have to compute this integral. I don't want to do this, I can't do this. So I'm going to draw samples according to the distribution with which x is found. And I will compute the function at those samples and average them. Okay? So that's a very standard result. So you draw samples, you compute the function, you average it. Okay? Where are we going to use this in options pricing? So I just said over there that my current value of this European call option or any option is a discounted version of the expected value of the payoff at time t. Yeah? So there is a payoff at maturity, and that payoff is a random variable because it's going to depend on what the stock price is going to be. Yeah? Plus other things in more complex options. So that random variable will have an expected value. Discounted is my current price that I'm going to think about. Okay? So now, in the simplest case that we looked at, in the log normal case, yeah, we said if we start at S0 and assume a geometric Brownian motion, then after time t, it's log normally distributed. We know the mean and we know the variance. Yeah? So I can write the distribution that happens at time t in this form. We had this formula before. This S0 times e to the power, that term becomes the mean, and that's the variance. Sigma times t, sigma squared t is the variance, and that's normal distributed random number. Okay? So you want to be able to look at this much. Forget the minus k for the moment. You want to look at this much and understand that this much is the possible values that I hit if I run the time series. So that distribution. Yeah. So I would sit here, this is my S0. If I run the process, I can be here, any of these places. Why would it be any of these places according to that equation? In that equation there is a random term, epsilon. Okay? I subtract k from this and max it with 0. That's the payoff of the option. Yeah. So there is an expression that tells me what the stock price will be, and that expression is a random term because it has in it a random variable, a random number. Subtract from k and max with 0 is the payoff of the option. We wrote this last time. Up to k it's 0, and beyond k it's linear. Okay? So this expression is a way of computing the option price. Because I know this f of t, and then I discount this. I compute the average of this one, discount by e to the minus rt, I get the fair price of today's option. Okay? With me? Okay. So there's a piece of code that does this, and maybe we can just quickly look at this. This function is from, almost all MATLAB code that I show you come from the textbook. Okay? How many of you have seen the textbook so far? Or not textbook, Brand New Mark textbook. Small number. Do we have enough copies in the library? Do we have a PDF? We never have enough copies. If I say it's a course text, there's buy one copy per 10 students at least. You know, is there only one copy or? You may not want to say this if you're not recording. If you look hard enough, you will find a PDF of this book. Some people are nodding. Have those who have not found the book seen the people who were nodding? Okay, so anyway, so the things that I'm copying, you always have this, but you should find the book. Oh, right. Okay, it's more than that. The code. So if you look at the author's name, you will find his web page, and the author's web page has all the programs that go with the book. Okay, so that you can actually download the code that's here. Anyway, so what we want to know is the structure of how one implements this. Okay, and so this is just a function. It takes in the current value of the stock, the strike price, risk-free interest rate, the time at which maturity happens, the volatility, and a number of samples with which I'm going to represent this distribution. Yeah? Not just one sample, I'm going to sample this. So what it does is generate random numbers of that many random numbers. Okay? And if you generate that many random numbers, then you are evaluating this expression that many times. Yeah? And the rest of it is just programming. You don't want to keep multiplying all the time, so you define a variable, you define another variable, and there is a e to the minus rt is the discount, there's the max operation, there's a 0, and that's our stock price in n rep 1 times, yeah, those many samples, subtract k, and max gives me the payoff function. Yeah, and if I average that, then I get the price. Okay, so there is an idea. There is a little piece of code that does it. Okay. What you want to really keep in mind is that there is that epsilon term here that tells me there isn't a single solution to this underlying stochastic process. Yeah? Because every increment is stochastic, so as these stochastic increments accumulate, at the point of interest t, capital T, I have a distribution of points. And through those distribution of points, I compute what the payoff might be. I compute the average of this and discount. So whether you discount before or after the average is the same, so it doesn't matter. Okay, is that doable? Clear? Okay. Okay, so you can write this function and you can test this, and if you are reading the book, they do a little clever thing that they set a random number generator state to 0, so that every time you run something, you get the same results. Yeah, so if you want to compare, computers have pseudo-random numbers, and you can force them to start at a particular seed point, and if you seed it by setting the state, as soon as you look at it, it should be fairly obvious to you. So when you do this kind of thing, when you generate random numbers, when you numerically average them, and then you make an inference from this, what are things that we need? There are two things that we will need, and I'll just mention them and give you a couple of examples of them. We won't go deep into this subject. It's a very rich subject. Okay, this much I can tell you. Sampling from probability densities is a huge subject in statistical inference. We will touch on a couple of them, and just to give you a feel for what's going on, and then we'll close this subject and move to time series analysis, the third topic that I want to talk about. Okay? So what are things about this approach? Maybe that's a bad title, but never mind. So if I call that function, so here I said I have this function, I'm calling this way and getting an answer. So if I call it this way, the price that's computed as an average is 1.2562. That's the answer that comes out. Yeah. The first thing we would observe is that if I run it many times, once, twice, 3 times, the answer is every time different. Yeah. This you would expect. Why? Because I'm generating random numbers, and I'm computing something out of them, and I'm averaging them. If I did it again, I get a different answer. Did it again, I get a different answer. Okay. So then I think maybe I could blow up how many samples that I take from here. Yeah. So instead of 1,000, if I took 100,000, or is it a million? I don't know. I count 1, 2, 3, 4, 5, 6 years. Take 1 million samples. then I again get different answers, but what would you expect about these answers when compared to those answers? Yeah, the variance of this will be smaller, the variability will be small. Yeah. Hopefully in this particular case, this would be an unbiased estimator. You know the terminology bias and variance? Yeah. So variance is every time I do an experiment, what sort of different answers I get. Yeah. So if I want to know how popular the Prime Minister is, I go and do a survey. And if I did a sample survey, it comes out the Prime Minister is 40% popular, has an approval rating of 40%, call it 20%. Yeah. Next time I do it, I get 22%. Next time I do it, I get 18%. Yeah, it's different. But if I increase the sample size, if I go and sample not just 50 people, but 1,000 people, then the variation I get around 20 will be small. Okay? I can talk about bias in that setting. Bias would be if I do all my sampling by email, so electronically, then I will lose people who will have no access to internet, say. Yeah. Or if I restrict myself to sampling in the south geographically in a different region, then I will use a bias. So what I would like you to do, when you have access to this sort of thing, if you want to understand what's going on here, is to cut and paste this and get yourself this function, and then run it with not just 3, but about 100 different runs. Collect all these answers that come out, and plot a box plot or something with 1,000 and 100,000, stack them next to each other, you will know what's going on. Yeah. Okay, so then there are things that we need when the distribution becomes more complicated is what are ways of sampling from these distributions, and what are ways in which we might control the variance. Those are the two important things that come to play. Okay. So sampling, very classic way of sampling from some arbitrary distribution which has a parametric form. If the function is writable as a particular form, then you would draw a random number, it's 0, 1, in 0 to 1, and then you return the inverse of the cumulative function. So that's the density you want to sample from. You want to produce a sample whose probability density is like that. This has a cumulative distribution which goes from, fx goes from 0 to 1. Yeah? And if you return the inverse of this, those inverses you collect will have the same density as f of x. Is that kind of intuitive? Can you think about this? We won't formally prove any of these. So if we think that it kind of makes sense, then it's okay. Yeah? We won't formally derive any of these. So suppose I have a probability density looking like that. So that's my f of x. My cumulative distribution, that's going to be like that. Yeah, with me? It goes from 0 to 1, somewhere in the middle. Well, assuming this is symmetric, this will be about 0.5. Yeah. So what I've written there is that if I generate random numbers in the range 0 to 1, and return f inverse u, what I'm saying is I will generate some random number, then I look up this way, and then go that way, and return this as a number. Okay? And if I keep doing this uniformly, then I will generate lots and lots of numbers here, and they will have the distribution that looks like that, density that looks like that. Okay? And you can compare that, suppose if the density is very broad like that, then sorry, it's obvious that the cumulative function is going to be what goes up very, very slowly. Okay, so now if I generate uniformly between 0 and 1, then the chances of generating something in this region, yeah, would be the same as the chances of generating this uniform random number in this region, which would be very small. Yeah, I would generate a lot more here because in this region would be seen a lot when I generate here uniformly. You with me? So uniform here, project, invert, you get something along this distribution. Okay, so that's the proof of this. Let's skip the proof for the moment. Not for the moment, I'm not interested in the proofs. It's there for completeness. So there's a nice example taken from the book. If you want exponential distribution, then you can sit down and integrate the exponential distribution, get the cumulative. You can manipulate the algebra and get the inverse to say if f of x is uniform, then what should I return? Okay, that's the way to work this out. So someone gives you, this is the distribution I want you to sample from. You've got to be able to do this step of integrating that to get the cumulative function. You've got to be able to manipulate the algebra to get the inverse. If you can do both those, then you can generate samples according to the exponential distribution. Yeah? So this is what you need to know. That if you want to sample from a particular density, i.e. generate samples according to this density, you've got to know what the cumulative distribution is, and then you've got to know what the inverse of that is. Yeah? The algebra of the stuff that I've sketched here. So this is only possible if we work with densities where there's a simple parametric form, and I'm able to integrate them, and I'm able to invert them. Okay, this may not, sorry.
Why do we inverse?
So the inverse is what I was saying here. So what I sketched here, as I generate a number between 0 and 1, and then I compute at what value will that number be reached by that function. Yeah, okay. So, okay, back again. My job is to generate a number, yeah? And if I generate many numbers along this axis, they should have this density. Yeah? What that means is I should be generating a lot of numbers in this region, very rarely one here, one here. Okay? So how do I do this? I uniformly generate numbers here between 0 and 1 with equal probability everywhere, equal probability in any tiny range. And then for each number I generate, so say this is 0.3, yeah, I invert the 0.3. I ask the question, at what value of x will this function have 3? 0.3.
That's y.
Yes. Okay. Okay, so this is just one way. It's well known, but it only works if you can do the integral if the density is in a parametric form. So here's another way. What you can say is if my function is not easily manipulatable in an analytic form, there is an acceptance rejection method. What this does is take another function t, yeah, which is always bigger than the function of interest, the probability density of interest. Yeah. So if I thought f of x has some shape, I think of a function which is always bigger than this. And that function I normalize and turn into a probability density. Okay? So now this is something you can figure out. So if t of x is some function, I take this function, normalize it by the integral in that whole domain, then this becomes a probability density. You happy? Also assuming that it's always positive. A function that's always positive, I compute the area under it by integrating all over the place, divide the function by that number, then I can think of this as a probability density. Yeah, because I need two things for something to be a probability density. It should always be positive. It should integrate to 1. That's all I need. Yeah. So you give me an arbitrary function in some area, some region. I would find the area under this, scale the function by that number, then I have a PDF. Okay? So what we can think of doing is that think of another density like this, generate variables, random variables according to that density, yeah? And then think of a uniform random number. If that uniform random number is less than this, then the sample that you want is this one, otherwise I repeat this. It's better if you look at this picture. So how do I do this? So I have a density f of x. Yeah? And what you have told me is bring me 1,000 samples that are distributed according to f of x. That's the contract. Okay? So the way I would do this, so here's one way you can do this in this acceptance method. is to think of, because I know you have already told me this fx is the function, I look at this and say, oh, this is only valid between 0 and 1. Yeah, it's not going anywhere else. So between 0 and 1, a function I can think of as being always bigger than this is I draw a horizontal line at its maximum. Yeah? So this t of x is a function that satisfies what I want here. Okay? And that's a uniform function. So what I will do is uniformly generate random data, okay, and ask the question if this function value I compute at that uniformly generated thing is bigger or smaller than normalize this one. Okay? So think about this. If you are at A, if the number that you generate is A, then there is this ratio of this height to that height is the chance with which I would accept A. Yeah? So in a region where the function value is small, that ratio works against me, and I'm more likely to reject that sample B. Okay? So I'm more likely to generate A than B in this region. With me? Now, if you have not understood this, here is the way to do this. This apparently is a total density. I haven't checked this out. Okay, so this is in one variable in 0 to 1. There's a squared term, cubic term, and fourth power term. And the book claims this is a probability density of 30. So this what that should mean is if you integrate x squared minus 2x cubed plus x to the power 4 between 0 and 1, you should get what? So for that thing to be a probability density, if I integrate x squared minus 2x cubed plus x to the power 4 between 0 and 1, that should be 1 over 30. Yeah? Apparently this is true. I haven't bothered to check it, but obviously you're going to do this tonight. So that's a little density. Yeah? I think the shape of this will look something roughly like that. So the way one would sample is to generate two numbers, look to see if the second one is smaller than this. Why is that 16? I do not remember. Why is that not 30? Yeah? In the 0 to 1 step, that is a, so this t of x has to be divided by the area under this curve so that it becomes 1. Okay, so I'm going to leave you to figure out why this is 16. Yeah? By the look of 30 or 1 over 30, one of the two. 16 doesn't make sense to me. So that's homework for you. And an even bigger homework is this one. Yeah? So you are given a function. Draw the graph fit, simulate 1,000 samples from this one. Yeah? Draw a histogram, and if you draw the histogram on top of that function, you will see how well you're trying to approximate that. Yeah? Do that with 100,000 samples, you get a better approximation. But look for the following, and this is the key one, because we can understand that if you ask me to draw samples according to some distribution, I can think of drawing samples according to some other distribution and accept or reject based on the ratio. Okay? And if I keep doing that, if that ratio is small, I'll be rejecting a lot. Once in a while, I'll accept. If the ratio is high, I'll accept more. Okay? So in regions where that ratio is high, I'll be accepting more. In regions where that ratio is low, I'll be accepting less. And my answer might be correct. That kind of intuitively makes sense. That's the first level of understanding. The second level of understanding is how many times might I be sampling before I accept something? And what's the average? Okay? So if you went and constructed this, given that it makes sense, constructed this with this t of x set up here, which that also satisfies this condition, right? It's bigger than any part of fx. Yeah? Then I'm artificially constructing something that will most of the time reject my samples, but if I sit there long enough, I will still draw samples according to this density. Okay? So there was a line that I wrote that had gone under the curve, under that, which is very good because now you can figure this out. So this is for you to figure out, on average, how many times do I have to do this trial before accepting a sample? Yeah. So if you just program it, you can just count it. Okay? And the answer to this one is C. That's C. Okay. So confirm that it's true. Okay, so that's one. So there are a couple of, we touched on a couple of things by which we can draw samples. Once you give me a distribution, I can draw samples. If it's a very nice parametric form, I can do it elegantly. If it is not a nice parametric form, I can resort to some technique like this to do this. Okay. The other point that we want to have is variance reduction. So we said if you do the experiment again and again, you get a different answer. Yeah. And that's variance. This you want to be small. Yeah. You want it to be small because I'm a polling agent and I want to do a survey and be able to tell the newscaster that David Cameron is 30% popular. Yeah. But if there's a big variance on this, then the quality of my estimate is bad. Yeah. And BBC may not call me next time. That's the kind of thing to think about. Okay, so we'll rush a little bit. So if you thought I have samples xi drawn independently from some underlying distribution, we know that the mean is the expected value. You can estimate that by averaging samples drawn from there. This we know. We know that the variance of that sample, given a sample size, is divide average xi, take away the mean squared. Okay. So every sample, how much does it vary from the mean? Squared average gives me the sample variance. Okay? And somewhere in deep, very deep in statistics is the knowledge why we have n-1 and not an n. Yeah, you're with me with that? And that refers to the term bias. We won't go into the details of this. Intuitively, just think of it as, when I estimate the sample variance, the mean is something that is not known to me. I have estimated the mean from the data. Yeah? So there is 1 degree of freedom less in what I can do. Yeah? This induces a bias. If you estimate variance with 1 over n, because that's what the basic intuition will tell you to write, yeah? Expected value is average. So I take n data, I have to divide by n. Yeah? And that induces a systematic bias. And that systematic bias comes from the fact that the mean has also been estimated from data. Okay, so the way to correct for that is instead of dividing by n, you have to divide by n minus 1. This is wrong. And if you have pocket calculators, there are, there's a statistical buttons, you will have a sigma n and sigma n minus 1. Have you seen this? Yeah? Aware of this? Yes, no? Yeah. Okay. Good. So we can now think of the error that we make in the estimation. So comes out as, of course, how much does my estimated average differ from the expected value, which is the mean. And this one is the variance of this one. Yeah? Because every time I do an experiment by averaging numbers to estimate the mean, I get a different answer. Yeah? So how much does this vary from the truth? So that's the variance of this one. So variance of this one, I just plug in the formula that I used to estimate in here. Yeah? And from here, I can go here. So how can I write this one? So variance of a sum of variables is the sum of the variances. Okay. So if I have n data points summed, then the variance that I get here is n times sigma squared, because each one has a variance sigma squared. Variance of the scaled version of a random variable, yeah, is the scaling squared times the variance of the random. Okay? So that comes straight from the definition of variance. If you add variables, the variance adds. If you scale it, it scales by the square of it. Okay? If you don't believe me, generate some random numbers, yeah, you will be convinced. We don't need formal proof, we need to be convinced something is true. Okay. So what happens then is that the quality of my estimation depends on the variance of the data scaled by the number of samples that I have. Okay? So what that immediately means is that if I want to be more and more reliable about David Cameron only being 20% popular, I will keep increasing the sample size. Yeah, so as I get more and more samples, the quality of my estimation linearly goes down. Okay. I can do more than that. In this context, where I have generated lots of samples, and I'm going to divide by n to tell you what the quality of what I have done is, I can either improve my quality by increasing the sample size, or by being clever about drawing samples that have a low variance. Yeah. And that is another huge body of literature of techniques to reduce variance in simulations and estimations based on simulations. Okay, it's a very big body of literature. We'll just touch on it. I'll give you an example and some code which you can play with to figure out that this might be true. Okay? It's just saying the same thing. So one particular way of reducing variances is called antithetic sampling. So remember, what did we do? We generated lots and lots of samples, and then we averaged them. Yeah? So in this technique, what you do is you generate lots of samples, but in pairs. You have to make sure that the next time you generate a pair, you're doing it totally independently from the way you generated this one. Okay? So you have a sequence that way. And there's a second sequence which is horizontally independent, yeah, but vertically between this x11 and x21, there is some functional relationship. Okay? And then it turns out you can cleverly construct these relationships by which the variance of that data will go down. Variance of the samples you have drawn will go down, which is what this trick is. So xi, x1 and x2 of each column have some dependency. And then what you use as a sample is a function of each of these pairs, function of each pair, okay? So I'm going to now estimate the mean that I'm after by averaging x of i's, but each of these x of i's were generated in pairs and averaged. Okay, so this is something you can construct. Just based on this description, you can do this. But if you were to do this, what happens is that you can show that the variance of interest, variance of the estimates, yeah, turns out to be 1 over 7 times the variance that you have, times 1 plus rho, and this rho is the correlation or covariance between those two rows. So instead of generating a bunch of samples and computing my inference from it, I generate pairs of samples. A function of this gives me the base from which I'm going to estimate, and by constructing correlations between them, I can reduce the total variance. So if I had constructed that row and this row to be somewhat negatively correlated, yeah, then my total variance is whatever I have, 1 minus that row. Okay. So that's the idea. The very high-level idea is that variance is important. You have to reduce variance. That's what the quality of the estimator is. There are very structured, neat tricks to do this. Okay? So we are only seeing a very simple feel for it here. We can take it to how we price options. I've given you 2 pieces of code there. You will find this. This is what we have done before. We have generated lots and lots of random numbers, worked out what the option prices might be at those values of random numbers. Max with 0 after taking away k is the payoff. Discounted payoff gives me the yeah. So here I have many, many discounted payoffs. There's a function normal fit, which would fit normal density through this payoff and give me an average and a confidence interval. Okay? And this confidence interval is what? Similar to variance, similar to the quality of the estimate. Okay. So this can be done in 2 ways. One is the naive way that we did before. And there is another piece of code that does it by generating a set of variables and an antithetic set of variables, and then averages the payoff. Okay, so this you can play with and will convince yourself that the resulting confidence interval is smaller. Okay, so very quickly in the next 2 minutes, so we have done 3 ways of looking at pricing options. And in '94, these guys came up with a very nice paper in which they said, this is a difficult or complex functional relationship, but this is something we can actually approximate with a neural net type model. Okay? And they used a particular type of neural net model, and the assignment 3 is to implement that. Okay? You can believe, okay, this is what you will achieve in doing this. So in terms of the time to maturity and the underlying asset price normalized by the strike price, what they did was they ran Black-Scholes model, yeah, with an assumed volatility and interest rate, and generated data. Okay? So the data they generated, you can see as little points, would be given the time to maturity, given the value of the stock price with normalized by the strike price, yeah, turns out to be distributed in some way. Yeah. Like the call option price corresponding to this is distributed about this way. And then you can train a model on this and fit a function through this, and this seems to be a very, very good approximation to the Black-Scholes model. Okay? So you can play with this by generating some data, and you will see how well this approximates, and that's the third exercise that you will do. Okay? It has a model like this, you will see. Yeah, I don't want to dwell on this now in the next minus 5 minutes. Monday in the lab, I'll tell you what this is, the story of this.